Well, this interview centers on the development of the MGO tunnel barrier used in modern TMR heads. Hard disk drives have survived as the information storage density device of choice because of sustained and steep advances in storage density. Density advances require downward scaling of key components. The reduction of the size of stored bits caused signal amplitude reduction, which necessitated the invention of more powerful detectors. Magnetoresistive heads were the successful answer. The third generation of MR heads introduced the phenomenon of tunneling to increase the change of resistance. The largest change of TMR head resistance has been achieved with the MGO tunnel barrier. This oral history records the history of the development of the polycrystalline MGO-based magnetic tunnel junction and the contributions to its success by Messrs. Naoki Watanabe, Hiroki Maehara, Koichi Terunuma, and Chang Park. Now we'll turn over to the questions. We'll start with you, Naoki, and could you tell us a bit about your background, where you were born, your name, background, where were you born, and where did you grow up, some of the schools you went to. Please go ahead.
Yeah. I'm Naoki Watanabe. I'm born in Japan, Yamanashi Prefectures. Then growing up during high school. Then I'm going to the Yokohama National University, then studying for meteorologicals. Then, but in childhood, I'm a kind of I like to architectures, but so I'm going to the material side. So in universities. So that's kind of stories. Yeah.
Good. So how do we, would you like to go ahead next and give us your background?
Okay. I am Hiroki Maehara, and I was born in Tokyo, Japan, and grew up there. And I graduated Tokyo Denki University, and I was researching for the electrical circuit, and I joined the Canon Elba at 2002, and after joining the Canon Elba, I researching for the deposition process for the magnetic materials, and now I'm researching for the spintronics devices such as magnetic sensors and or the MRAM. Yeah, thank you.
And is that continuing at Canon and Elba, or did you move to a different employer?
I moved Tokyo Electron Limited at 2040. Yeah.
How about you, Chang Man?
I'm Chang Park. I born in Korea, South Korea, of course. Then I finished my PhD. Major was physics. When I was at 30s, and I moved to U.S. My government supported a 2-year postdoc program, so that I joined the material science department in Stanford University. And then I learned most of the state-of-art technology related with the magnetic thin film and vacuum science and all that thing. After that, I joined the HDD industry year 2001, and working all the way magnetic recording head sensor area. So that's today is the topic of the MGO sensor, MTJ sensor. Then I moved to Samsung for spintronics MRAM, STT MRAM area. Then year 2013, I joined the Tokyo Electron company, and I'm working for the STT-MRAM, which is again related with MGO, MTJ technology for spintronics. So,
And your first job in the industry was with TDK?
it was a read-write.
Read-write.
Yeah, in Fremont, California, head manufacturing company, recording head manufacturing company. And I was working on the TMR at that time, first job. Yeah.
Very good. And Terunuma-san?
Yes.
A little bit about your background.
My name is Koichi Terunuma. I graduated Ibaraki University and also grew up in Ibaraki Prefecture. I graduated in 1983 and joined TDK. And first, my mission is development of high BS, high flux magnetization, soft field magnet materials for head by sputtering. Next, I joined head division and development of reader and writer for advanced magnetic head. That's all. Thank you.
Thank you. And I think Watanabe-san, you went directly to ANELBA after the university, or did you work for other companies?
No, I'm working for ANELBA, joining in 1985. Then working for the equipment development for the sputtering, mainly for magnet optics, optical and hard disk equipment. And also the hard disk media and the head for today's subject for MGO fabrication tools. Then after the development, then I'm going to Tokyo Electron for to make another PVD tool development. Then now. Also, I'm still working for MGO process development right now. It's my life work, kind of, yeah.
It's a very important
Yeah.
development, right?
Yeah.
Could you tell us a little bit more about your current position at Tokyo Electron?
Yeah, I'm a project leader of advanced film project. So, and almost mainly for MRAM application, PVD tools. Then such multi-layer, it's a very common used. So very complicated multi-layer like tunnel junction. So we now developed also tool equipment itself, also process. Yeah, right
fabrication
now.
For the deposition.
Yeah.
I'd like to explore a little bit more everybody else's current position. But before we go there, if you think back, were there some people who had a major influence on your thinking about which field to study, what area to focus on?
After join the company, some company,
or even in the university, were there any particular professors or
teachers? Yeah. So most influenced person is Sasaki-san from Shodenko. So I joined to ANELBA in the nowadays. So Shodenko is the most biggest media company for hard drive.
Yes.
But at that time it's nothing. So then Sasaki-san starting then was a business for media. So I'm working very closely. So it's I'm learning from him many things, how to make it. So and most effective person, maybe all over this industry, maybe also.
Yeah, he seems to be a very strong leader.
Yeah, maybe you know.
Yeah.
Yeah. Yeah.
Terunuma-san, a little bit about your current position and any people who had a major influence.
Current position is spin applied device application group. I'm group leader now. I was influenced by professor at university. His name is Furukoshi. Already passed away. He's gave many influence.
Thank you. How about yourselves? Current position and
my current position is a researcher, and researching for the deposition process and the etching process for the MTJ or some magnetic materials. And my first boss is Naoki Watanabe, and I was influenced from him for the engineering, and I was collaborated with Professor Suzuki, who works in Osaka University, and he taught me about scientific thinking and researching a method for me, and I'm very thanks for him and Watanabe-san.
Very nice. It's nice to have you both together. And Chang-man, any?
Many people. I cannot thank enough to all those people. But if I come up maybe one or two, then my advisor from Korea, who teach me and who start me magnetics. So his name is Dogun Hwang. Mm-hmm. But he's not doing magnetics anymore. He's transitioned to the bio. So maybe he got enough magnetics. And then second important of my research or engineering life was Bob White from Stanford. Every morning 6:30 he show up in my lab and he greeting and kind of encouraging my research when we were together in Stanford. He gave me a lot of opportunity as a scientist at that time, and I can go anywhere in Stanford lab per his support and help. So not only the magnetics, but at that time I learned e-beam nanolithography, all that thing. So now that knowledge is very useful day by day of my technical marketing of my current job. So I wish I can meet him again. Yeah, but he's pretty old enough right now. He retired. So yeah, so those two gentlemen and scientists were my biggest impact on my career and life. Not only science but life. Yeah, I learned a lot from those two, mainly.
And if he came to the lab at 6:30 in the morning, when did you have to be there? Or you just didn't go home at night?
Yeah, it was too much fun because compared to my PhD time of a resource in Korea, compared to in Stanford, Stanford at that time already very advanced everything. So all the thing I look at the technical journal was available in front of me, right? So there was a kind of a big toy store for me. I enjoyed that a lot. Yeah.
And your current position is in marketing for?
Yeah, director of technical marketing, belong to Tokyo Electron Corporate. But again, my major was magnetics, and also spent time for read head sensor. so that I move around and promoting this STT-MM technology with the PBD product. So again, Watanabe-san, me visiting many other magnetics colleagues who working on the semiconductor memory for STT-MM. So every day is kind of a happy day. A lot of challenges, but yeah, still good.
Sounds like it was a very interesting experience.
Yeah.
Yeah. So maybe we could move to how did the interest in MGO and MTJ start? Maybe Watanabe, you can
Yeah.
start that.
Yeah.
How did you? I think the development happened while you were at Anelva, Canon Anelva, right? So
Yeah.
how did that start?
Ah,
Why were you
yeah,
and
yeah.
why was Anelva interested in the subject?
Yeah. I'm almost in 90 is almost media for the hard disk drive for media tools. So, but we also at that time I'm thinking for the head is also big need a big challenge for the high SNR for the high output for signal. So then that time also MRAM also becoming hot as at 2000 or around year 2000. So then so the very big requirement needs from a customer for the such a TMR head and JMR head to transit to the TMR. Also MRAM is using TMR MTJ. So I think very interested to these opportunities. Then the TMR sensor, but GMR is at that time almost 10% MR ratio. But TMR is a potential to over 50% kind of. So, and we are just very interested in that to improve the MR ratio. So in early 2000 to 2004, so struggling for alumina. So maybe all of researchers working for alumina TMR. Then what few percent improved and limitation for almost 70% for TMR ratio. So, but at that time maybe customer also industry needs more high MR ratio. So that time so Yuasa-san from AIST is working MGO, and also Alabama University's Dr. Butler is predict for over 1,000% for the MR ratio for the potential for MGO. So everyone very exciting for 1,000% MR is possible or not. So everyone working, researcher working. So also I'm working. So at that time, so Yuasa-san shows over 200% for single crystal MGO. Then, that's possible for over 100% is at that time is very surprised. 100% over, and take 200%. So that's very interesting and exciting. So now at the time I'm working for, but that Yuasa-san technique is very high temperature for the single crystal deposition. But industry doesn't like such a difficult process for the tough high temperature process. So now then we are thinking how to make it to the industry how to contribute to the existing at that time existing product. So and then so at that time, so Maehara-san working for AIST, and we at that time, so we I think we ordered more close to the industry-like process. So and he is working for like developed a new cobalt ion boron amorphous process. It's a room temperature. It's nothing to changing existing process. So cobalt ion boron MgO cobalt ion boron sandwiches. So it's a very unique. And then published paper. Then all of customer interested to over 230% MR ratio achieved. Then so it's almost industry very excited. It's so over alumina is 70%. It's 4 times jumping. So maybe so at this jump is very good for the hard disk recording density improvement. So yeah, so I think it's just some many opportunity like Butler-san present 1000%, US-san present 200% single crystal potential. So then so my thinking is how to contribute to industry. So it's a very good opportunity, such kind of exciting time.
The work you did, Maehara-san, in the university was on the single crystal. It was amorphous electrodes, but still single crystal MgO, or was it polycrystalline, the MgO?
Okay, first we tried to make the single crystal iron MgO iron system by the PVD, but it's difficult to make for the industrial system. So we tried to change thinking, and we discovered MgO grows on the as a polycrystal on the amorphous cobalt ion boron, and but we need the epitaxial relationship between the magnetic materials and the MgO for obtaining the huge MR ratio. But we discovered such a phenomena, but not enough for obtaining the huge MR ratio. So we developed the combined deposition process and annealing process. We call the annealing process solid phase epitaxy process, and it was successful to obtain the huge MR ratio over the 200%, and it was very suitable for the industry technology.
Very interesting. So how did it evolve from that point? You have the exciting results in the university. You're interested in solving the industry's problem. How did it evolve from that point onward? How you just hired Maehara?
No. But just idea is ideally, copper-time boron is existed, but most surprisingly, is copper-time boron is amorphous. Then we check the published paper says it's MgO is a crystal, single crystal on the amorphous film. So single crystallized MgO, and that's I'm very surprised. Why? Why MgO itself it make a single crystal on the amorphous? Usually, so need a texturing before MgO deposition for the single crystal ion or other material. But amorphous on the MgO is very surprising. So that no one maybe understand that time. I'm also cannot understand why MgO single crystal. So that's very funny now. But Maehara-san make kind of films, yeah.
But you then apparently were able to refine the process till you made one that you thought would be satisfactory for the industry.
How you means for?
Well, I'm trying to bridge from the early work and the exciting results to how did the process then and design of the MTJ migrate to the head companies. Right?
Yeah. That time, so we need to publish the paper first, so then to let every researcher or also maybe customer want let them know so early as possible. So we make papers. Then that's maybe very easy to make a customer side. So I think so. So I'm very quickly so make papers. So to yeah.
Well, you Chang man, and you were Koichi were in the receiving end of this in the head companies, right? How do you see it from your perspective? How did the MgO know-how and migrate into practical heads? Did it come indirectly to you, or did it come through an Elva? I'm just trying to figure out how the process and design made it.
Yes, Elva informed us the MgO shows very high MO ratio. We also understood, but the resistivity is so high at the time, double digit. For head application, single digit is necessary. But soon resistivity reduced to single digit and also show high MO ratio. And TDK decided to prepare the actual head to using MgO. So we asked Elva for the test deposition. The result is so promising. The output signal is 3 times or much more than 3 times larger than aluminum oxide MTGA. TDK presented TMR seed year 2005, first report of MgO reader. But the output signal is so high, but the also shows very high noise, Barkhausen noise or random telegraph noise, so on. So we started tuning of stack configuration such as layer composition or layer configuration to reduce noise. For example, the magnetic restriction of free layer. First, MGO used cobalt iron boron, so thick layers, but we tune the free layer composition and free layer configuration to reduce noise. And also, we already have had a know-how of free layer configuration for aluminum oxide MTJ. At that time, it's not so difficult to tune up. Though we succeeded, MGO MTJ and shipped heads for our customers to year 2007.
Could it be that TDK's TMR with MGO was the first head in the industry?
Our understanding is so.
Okay. And Chang-man, where were you at this point in time? Remind us. Were you at read-write or?
No, at that time I was Western Digital. Yeah, 2003, 4, 5. So that was the peak time of the MGO development. And of course, we were competing with the Terunuma team for MGO development. Everybody was surprised from this technical journal was published by Anelba and Yuasa-san jointly. So because the TMR ratio was amazingly high. But again, like Terunuma-san described, the read head business is not only signal but also noise we need to control. Then they were silently, engineering in their shop, in R&D shop. So everybody were very quiet. But whenever we go to an international magnetic conference, then every topic was MGO related, because everybody enjoying this high signal and MGO technology at that time. So we were very somewhat afraid because it's too amazing. But on the other hand, we were very confident that this would be the next generation read-ahead technology. So we were enjoying at that time as an engineer and researcher of this MGO, kind of innovation at that time. Yeah.
I want to just clarify, pin down some of the numbers. I think you said, Watanabe-san, that the maximum resistance change for the GMR was about 17%?
Yeah, 15.
17, right?
Yeah, 17
or
15, yeah.
And the early MGO TMR heads had 3 times that value. Right?
Yeah.
And what was the main breakthrough that enabled the reduction of the resistance? Was that modifying the stack by adding an MG layer under the MGO layer, or what reduced that resistance?
MGO thickness, because MTJ resistance is depends on the tunneling barrier thickness, so we must reduce the MGO thickness.
Was that the only main mechanism? Because I remember reading some of the papers on the stacks, the MGO junctions, and the MTJ junctions, and it looked like, in addition to having a magnetic electrode, one also deposited a metallic magnesium layer, right? And then the MGO, and what was that extra MG layer for? Do you remember? I thought perhaps that was also for impedance control.
In the TDK case, we use natural oxidation. MEG, metallic MEG. And also aluminum oxide MgO, MTJ also use natural oxidation.
Okay.
The plasma oxidation is so strong.
Very good. And so the first heads shipped in 2007. And then how quickly did the industry switch to
Yes, so quick.
MgO?
So quick.
I imagine everywhere. Do you remember you were at WD? It also happened quickly.
Hitachi GST. 2005 I moved to Hitachi GST, so it was a boundary of this MgO introduction as a production. I think in 2007 most head manufacturing company or HDD company start productioning this MgO read head, because it was a huge competition, because not only the SNR improvement but also other following yield improvement and all, it was kind of a free gift, so that every HDD head manufacturing company start making production around 2007 and 8, something like that. It was so quick.
Nobody could afford to miss it, right?
It was too sweet.
But HDD is, I mentioned, industry itself is very dynamic. Maybe Chris-san knows. And new technology is published very, very quickly to the product for the hard drive. So it's I know the semiconductor business and also other flat panel, but most dynamic industry is a hard drive.
Hard drive industry.
Very, very quickly changing for the new technology introduction. Then maybe Park-san says it's almost very one year. I don't know, but very, very quickly changing all of.
It may have been one of the fastest transitions. Right? In the industry. It sounds like it was about in 1 year. We switched from aluminum oxide to MgO. You all talked a little bit about the interaction between the university and industry, right? This may be a key example of the value of that kind of collaboration, right? Because can you talk a little bit about AAST some more? Was it strictly focused on magnetics or other subjects too?
AAST, so Yuasa-san, Professor Yuasa's group is focusing on spintronics, not only hard drive for MRAM application development, very early stage, 2000 around. Then, so we know we are at that time. So many paper we are working collaboration with AIST and ANELBA. So then that also Maehara-san involving. So he's just Yuasa-san thinking, and also Suzuki Sensei from Osaka University. Suzuki Sensei also located in the AIST. So, and his idea is image is very close to the industrial mind. So how to supporting, how to contribute industry for hard drive MRAM. So that's very good for the working with AIST. Some professor, like a university professor, is far away from the existing product. So, and but in the Yosan group, Suzuki Sensei is very close to the industry. So we, I think that time, so we are working with AIST. So very good synergy, good collaboration. So I think
it's an exceptional case because it's. I know of many joint university industry efforts that try to achieve such success, but I know it's very difficult. So it's very positive that AIST was able to contribute like this and help make this happen. Well, let's see. I think we covered most of the ground. Any opinions about the outlook for the future of MGO, or are we going to have to invent a new tunnel barrier? What do you think?
I'm personally so in almost over 10 years for the MGO. So in the industry is mainly still focusing on MGO, not only the hard drive for the MRAM, also MGO barriers. So it's currently it's no choice. It's a very industry friendly process for MGO fabrication right now, I believe. So other also material, not only MGO, but everyone researcher working. But no choice, I think, right now. Then future also MRAM coming in case, so it's only MGO right now. So and MGO barrier is still mainstream for the future or for the tunnel junctions, I think. Yeah.
Looks like a very good, solid invention, right? Discovery. And, no one has yet invented anything that will be superior.
Yeah. How do you think?
So, I mean, MGO is a kind of gift for this research area and also industry. So I'm now working for HDD industry and semiconductor industry and also non-semiconductor industry. Those three areas. Right now, everybody talking about we are hitting the Moore's law, the war of the Moore's law.
Yeah.
So you cannot put any more than many transistor. We are hitting kind of technology war in semiconductor. So a lot of people start thinking in a different direction, like spintronics. So, but this spintronics already started from the HDD industry long time ago.
Yes.
Right. But when MGO came, this make more variety of the application and interest and phenomena in magnetics and spintronics. Then now semiconductor people start adapting it. That is STT-MRAM and also beyond STT-MRAM. Which is very, very promising. Yeah. I mean, year 2000, a lot of industry and company players start MRAM, but at that time was in-plane type of toggle or field generating MRAM. But now, almost everybody start using MGO tunnel junction for their STT-MRAM. And then not only semiconductor STT-MRAM, but also the automotive sensor, and also HDD side also still shrinking and trying to make it smaller and lower. So this MGO is a kind of gift for all the researcher in this entire industry, and without we knowing it, maybe there's many MGO, MTJ around us already. One thing is, so far, there's no new material which is very industry friendly and also fundamentally strong enough, this spintronics. There's no replacing material rather than MgO, magnesium oxide, yet so far. So maybe I cannot say the exact number, but maybe another 10 years, like we went through, MgO can be popular and then using as a main technology core source, I think. Yeah.
I hope you're right. I hope it has, it sounds like it has the potential to have a very bright future. Anything else that we should cover before we end the interview? Any other subject that you'd like to discuss or?
No.
Well,
But,
I want to
yeah,
thank
yeah.
you very much
Yeah,
for giving us the opportunity to interview you in about this important development, the importance of MgO, and it's doubly good to know that it may have potential to penetrate a variety of technologies, not just TMR heads. Thank you very much.
Yeah.
Thank you.
Thank you
Thank you.
much.